quantitative Bill Ward, an active member of NEMETODE group, and somewhat of a specialist in the whole area of meteor spectroscopy. And you've seen Bill's and how he has advanced over the last number of years. He's taken on this project is spectacular. Just kind of love the Bill producing, and certainly has inspired me to try out spectroscopy myself with my own couple of cameras. So without further ado, take it away.
Thanks, Michael, and thank you for inviting me over. There are a couple of caveats here, because meteor spectroscopy is as frustrating and difficult as it is rewarding, but it's the key physical analytical tool we have to examine the composition of materials. Now, nature provides us with several either good fortune or cruel twists of fate, depending on your perspective. The meteor itself is a small, tiny particle minding its own business when it encounters the Earth's atmosphere, and then after a lifetime of tens, hundreds, thousands of years, who knows, in that final second we get the insight into what that particle is made of. And that, combined with all the other observations from the NEMETODE group and others, gives us a global understanding of what the meteoroid is, what it's made of, where it's been, possibly where it's from. So spectroscopy is the key tool, and with meteors it is particularly easy to do. And that's perhaps one of these little quirks of nature. However, when I was reading up something completely unrelated, I came across a very interesting fact that the first meteor spectroscopy in the world was conducted from Glasgow by the grandson of William Herschel, a guy called Alexander Herschel. And he was a professor of natural philosophy at what was then called Anderston's College, which over time has become the University of Strathclyde. Now, in those days there was no imaging, it was all done visually, so there will be an observability function test coming up, so you need to wake up for that. So he designed his own spectroscope. It was essentially a pair of binoculars with some prisms integrated into them, which, when you looked through them, when the meteor happened, you saw the flash of light. And I cannot imagine doing it that way, but he was a very determined chap. The Leonids were the meteor shower of choice at the time. It began to become understood that 1799, 1833, there was a periodicity. Would there be a big shower in 1866? And there was a lot of work done at that time to observe the shower. So Alexander decided he was going to use this new technology to examine the Leonids. However, he decided, yes, to try the instrument in the Perseids. Now, I can't remember the name of the instrument maker, I'm afraid. It was a gentleman in London, and he got it in just in time for the Perseids. And on the peak of the Perseids, he actually observed several meteors, and they're actually recorded in the British Association for the Advancement of Science records. However, come the Leonids, which was the main event, he didn't see very much at all. It was cloudy and raining and very Victorian-type language. The weather was not conducive to scientific observing. The other interesting thing is, I think I can claim quite legitimately to be part of an unbroken chain of two observers spanning 140 years to do it from Glasgow. So that's my one claim to fame. I worked with a Herschel. Right, so back to reality. Spectroscopy relies on being able to split the light from your object of interest into its constituent colours. Normally done with very complex instruments in laboratory, so that's not really practical for meteors because they are just flashes of light in the sky. We then have to reconcile the differences in having a system which will allow us to catch a reasonable number of meteors, but at a tiny image scale where you don't see much detail, or a smaller field of view which gives you a larger image scale which you can see more detail in. And this is what you'll see throughout this entire presentation, that this field is one of compromises. There are so many observational variables, it's actually quite difficult to come to what might be an ideal system. And as I said, one of the very properties that makes a meteor is something that we can exploit by good fortune. So we can just put some sort of dispersive optic in front of the lens, whether it's a grating or a prism. I and everybody else use a grating simply because they are mechanically easier to mount, but there is some more on that. That's pretty much one of my systems. I have 4 9-10 cameras with 12mm f.8 lenses, and it just so happens a 50mm square grating, because of Pythagoras, just sits beautifully inside a 72mm lens cap. So it's quite convenient just to assemble it in a mechanical sense. But I would recommend that you do incorporate some sort of heating element. I run my cameras completely unexposed. I'm a bit of a purist. I don't like any glass in front of them, just to prevent reflections and light getting scattered in from other sources. But disaster awaits the unwary. What I discovered was that when my timers all worked, I accidentally didn't set the heater to be longer than the camera operation. So the temperature continued to fall, the condensation formed and then froze. And actually this completely lifts off the grating, the replica grating from your substrate, and that is a disaster. Anyway, so the good thing about gratings is when you look at the mathematics, the light that's being dispersed through the grating is dispersed almost linearly, which means on your sensor, when you measure along so many pixels, it represents the same amount of nanometers in the spectrum. Prisms, on the other hand, don't do that. Just by the very nature of light passing through glass, the dispersion is proportional to wavelength, so the dispersion is then non-linear. One wavelength bends a little bit more than another, and that means the data reduction can be somewhat more complex, and you end up trying to guesstimate even more than we already have to do to get a result. But the unique thing about meteors is that they are essentially a line of light in the sky. Now that is represented in most spectroscopes as the slit you put on your source to determine the spectra. So we can imagine the meteor just being a line of light being dispersed through the grating, and if things go to plan, you get a nice ready to go spectra. Now, this is the test. So you imagine 1866, you're on the roof of Anderson's College in Glasgow with your binocular spectroscope. You're doing this visually. Can I get us to run? So, what do you see there? So you're going, what was that? And you can't do this. So what do you see? Very little. So yeah, these guys were determined. So this pretty much sums up the whole of meteor spectroscopy. The video systems allow us to gather the subsequent frames, combine them into a single image, which gives us the spectrum image here. To make use of that, you've got to do a bit of pre-processing. You've got to get it into a form that the software can handle. And that invariably means rotating the spectrum, then deslanting it, and a term that spectroscopists will be familiar with, desmile. And that's kind of borrowed in this sense as the curvature of the meteor through the field of view because of pincushion and barrel distortion, spherical aberrations. But the principle is the same. You've really got to kind of flatten out that line. And once you do all that, you end up with a sort of rectangular spectrum, which you can then import into the various software packages and produce the goods. But you need to be wary of little sneaky stars which can appear as little bumps and fool you. So you need to give it some sort of pre-inspection, make sure everything's okay. What the software does is what's called binning. So, my button gone. It measures the intensity vertically and adds up the pixel count, and allows you to drag out quite weak signals actually in occasion. And you can produce a graphical representation of what you're actually seeing. And in this case, it's that there. So that's the raw spectrum. That's just a graphical interpretation of that picture. And in this case, we have these 5 bands are our best friends, because this is a nitrogen emission, oxygen, nitrogen, oxygen, nitrogen. These come from the atmosphere They are very stable, and if you get them, you can step back to find out what other lines are. But over time, you actually get quite accustomed to seeing the patterns, and that allows you to get a handle on what's happening actually quite easily with a bit of practice. But one of the other problems that spectroscopy has is the calibration of the image. That because the fall of the meteors in different parts of the sky, therefore it's a different distance from you, therefore there's different atmospheric absorptions, it depends on the efficiency of the optics, the blaze of the grating. It's absolutely impossible to get a fully calibrated spectrum. The best you can do is get some sort of arbitrary, sort of, I don't even know what the right word is. You want to just get it as close as you can to what's real, to allow you to get a relative comparison between spectra. So generally what's done is we divide through by a known calibrated source, which I tend to use Vega, because that's the one that's got the best known features in the various software packages that I use. The problem is that silicon, by its electronic structure, has what's called a band gap, and that means it's sensitive to longer wavelengths more than it is to short wavelengths. So when you divide through by a known flux source, it tends to enhance the blue because it's in the raw image, that's depressed because it's less sensitive, and it sort of suppresses the red. So this is technically more correct than that, but that is often more easy to interpret than that. And that little bump there, which, where it be there, it disappears there, but that's that star. So you need to be careful when you're looking at raw and corrected spectra as to what you're actually dealing with. And what's often done is that you can take the spectrums, run it through different utilities, and I use Visual Spec, and you can produce these nice colour bands, which I particularly like. The reason I prefer Visual Spec over RSpec is that Visual Spec just codes the colours irrespective of the wavelength. So anything longer than 700 nanometers is just red. Well, you can't see it, but it codes it as red. Similarly, down towards the blue, anything short of 400 just gets coded blue. So at least it gives you a nice visual representation of what you're seeing. But these atmospheric bands are very, very important. They're very, very useful. So you've got your camera, we've got our gratings. What can we see? Well, there are all the streams, and these themselves have their own particular characteristics. This is a Geminid which I recorded from Tenerife in 2017. A beautiful spectrum. In fact, it's probably one of the best Geminid spectra ever recorded. This is one of the oxygen line, the nitrogen bands, proportionally less sodium. Lots of magnesium, lots of iron, some more, that's probably calcium and magnesium there. But the interesting thing to note, there's just from that one to that one, is the sodium line is quite interesting, because the kind of standard theory is that sodium is preferentially removed from the meteoroid space through exposure to sunlight, cosmic rays. It's considered a volatile. So the sodium line is quite useful for determining the age. But as I actually put in a little post in the BA forum, how old is old? That's what you don't know. But it's an indicator that it's either been exposed to a lot of sunlight, which Phaethon is, or it's quite an old meteoroid. So again, is that old just because it's been exposed to sunlight, or is that old and not exposed to sunlight, or is it exposed to sunlight and not old? It's one of the things that we can't get. And then we have the Perseids, which come in faster velocity, and ultimately the Leonids. And I picked these four because on the software they were all approximately the same magnitude, about 0, -1. And the interesting thing to note is that the kinetic energy is proportional to the velocity squared. So when you go from the Geminids at about 35 kilometers per second to the Leonids, you're doubling the speed, therefore you're quadrupling the energy, which actually means in reality that to produce the same meteor spectrum, there is only a quarter of the material in that as there is in the gem I just showed, and that's why there are proportionally less lines, because there's actually less of it. And then you can just run them all together, and it just gives you a nice representation of how the spectrum lines all match up. And the greater the area under the curve is an indication of the amount of energy the meteoroid has when it becomes a meteor and glows in our atmosphere. The other interesting thing is this change in the sodium. Now, whether that is real or relative, I don't know, but it's something which we'll come to again towards the end. Another meteor stream is the Lyrids from last year. I had quite good luck. What surprised me since I've started doing this is that a lot of the meteors are made of the same stuff. It's mostly stone, so they have the same elements over and over again. But there are very subtle differences between the meteor streams. But when you actually get several ones of the same thing together, it is surprising how similar they are. They all show the same sort of relative proportions. They all show the same features. So there is some intrinsic similarity in the material that's shed by a given body that produces these showers. So the Lyrids at 40 kind of moderate shower, so there's relatively less atmospheric admission, but we're beginning to see some more of the metals coming up in the blue end. I'm going through this quite quickly since we're running out of time. But there are some other things which I wasn't expecting. Having observed thousands of meteors and hundreds of spectrums, you get the impression that the meteor comes in, glows brighter and brighter and brighter, and then ends. When I caught these and I was actually reviewing the videos the following day, what surprised me is that was not always the case. Some meteors came in, full brightness, and then faded away. And just by chance, I caught both of these on the same evening, and they're kind of faint, but they have quite unique signatures. And when you run them through the process, these lines are almost entirely iron. That one's a bit fair, that was the second fainter one. Possibly chrome, possibly nickel. Some of them, the metal elements have a very complex electron structure, and sometimes it's difficult at the resolutions we work at to be absolutely certain, which is another problem. But they are similar enough to say, yes, they are the same stuff, and the lines are close enough to established reference spectra to say that these were nickel-iron meteors. Now, that in turn, if you work it in reverse, gives you an indirect tool which you wouldn't know about unless you had the spectra in the first place. Is that if you see a particular light curve, you can now say, well, actually that's not just a stony meteor, that's probably an iron meteor. So you don't even need to have the spectra now, because we know we've got fingerprints which indicate that's the behaviour. And what it actually is it's the refractory nature of the stone. As a stony meteoroid comes into the atmosphere and ablates, it's fast, but it's a finite amount of time for the heat to get from the surface to the inside as the kinetic energy is dispersed and just basically atomises the meteoroid itself. Iron, the thermal conductivity, is significantly higher than stone, so it heats up like that. So it begins to glow as soon as it reaches a critical temperature, and then ablates away. And so we have an indirect way of now determining what an iron meteor is from other meteor observations without actually having the spectrum. But we wouldn't have known it unless we had the spectrums to start with. So, an interesting spectra, and this is another one of these ones that just comes up from time to time. And this one is particularly interesting because Michael has caught one of these, and I have since caught a second one. Another indirect signature is that when you look at the other spectra, there are all these atmospheric lines which would be located about there. So right away that tells you this thing is moving very slowly, because it's not imparting sufficient energy into the atmosphere to stimulate the emission from the nitrogen and oxygen atoms, which are quite tightly bound. It has an enormous sodium line. So indicates that it could be young, a fresh sample from whatever source. A fainter magnesium line, that lovely band is also very characteristic. That's a group of iron lines. So indirectly we know, without knowing anything else about it, that this was slow. So that can tell you something about the orbit, the way it's interacting with Earth's atmosphere, which you wouldn't know. If you just saw that in the sky, it would just be a slow meteor, but you wouldn't really have a feel for how slow or why it was slow. And if you do the analysis, so a young and slow chondrite, because apart from the refractories of stonies, there is a significant number of metal lines. So that could be a stony iron. Don't know for sure, but we have a high probability that that's what the spectrum can tell us. And this is just from a couple of weeks back. This is just the last slide. The exact opposite. We have our friendly atmospheric lines, which tell us what the wavelength range and the dispersion is. And when you step back here, you get a very distinct signature from calcium, from magnesium, but absolutely no sodium. None whatsoever. This is the first spectrum I have captured which has absolutely no sodium. So this has either been exposed to very intense sunlight, or it's very, very old. And I haven't included any slides here, but perhaps I should have, is that myself and David he moved to Dunure, he was down in Girvan for a while. This is where the combined spectroscopy and orbital work is important, because that then will be able to tell us, does that go really close to the sun? Does it have a very, very small perihelion distance? And the result we got a couple of years back, which kicked a lot of this off, certainly the first in the UK, if not in the wider spectroscopy world. Because whilst there is a large professional body of work on spectroscopy, it's very specialised. I'm making this up as I go along most of the time, because there's virtually nothing in the amateur community. So this could be completely correct, or it could be nonsense, I don't know. But it's one of the things that we now have an opportunity to do something about, because the more people that do it, even though there are difficulties with the calibration, even though there are difficulties with some of the interpretation, what we have is, if we can get a sufficient number of reasonable spectra with good signal to noise, good spectral range, for the first time we can actually begin to build up a database of spectra. And the more spectra we get, combined with the more orbital observations we have, we are at the threshold now where we've gone from just novelty of a few years back to complete utility. And we can have a view of our meteoroid environment, which was science fiction 20 years ago. When you look at some of the books from the 50s and 60s, we have grand sweeping statements like spectroscopy is almost impossible to do, it's very difficult, and there are only, I think there was a Russian book, Fedesky, I think it is, I don't know if that's how you pronounce his name properly, but he says that there is only a few score of spectra. A good meteor shower, you can do that in one night now. I mean, we have the technology is now available that we can do things which were almost impossible a very short time ago. And it is easy to do. This is all done with UFO capture, so if you've got a camera UFO, you're almost there. The first time I tried this in 2006, I actually blue tacked the grating to the front of the lens. It wasn't very sophisticated at all. And the first night I tried it was a Leonid, boom, right away. And having tried it photographically for 20 years, I just thought, this is the future. And so with that system, so I'm saying it was a 12mm f.8. When you look at it from a spectroscopic point of view, the R value, there is a resolution which is that you're divided by your wavelength, is around about 600-700. With a low count grating, maybe 300 lines per millimetre, your R value might be about 50 or 100. But it doesn't matter. As long as you can identify the main lines, you can see the sodium, the magnesium, the atmospheric lines. Because of these indirect indicators, you're on the road to gathering information that can be incorporated into any future work that's done. It's the fact that we can do it now that's the important thing. One of the kind of gurus of meteor spectroscopy, a chap from the Czech Republic, Jerry Borovichka, he just released a paper, I think it was last year, and he had a classification of 70 basic spectrum types. And there are stuff that I have, in fact that's one of them, which isn't there. So we've got a new one already. We can do more and more spectro-orbital work. Work with Alec, we've got some results with Dave. That's a bit more luck oriented. You've just got to be lucky with weather at both stations sufficiently far apart that you can resolve an orbit and what have you. But that's developing. So if anybody wants to take part, it is relatively straightforward. The software is free. The most expensive piece is the grating, and unfortunately you just have to buy a grating. There are several suppliers, Edmund Optics, Thor Labs. You can use plastic film, which you get for a few pounds. That's not so expensive. You can go to borosilicate replica gratings, which are maybe £100, or you can go to the fused silica, which is very, very good in the blue, but that's several £100s. So there are different options as to how you can actually proceed with developing the system. But it is literally the case of just sticking something in front of your lens. I use UFO capture to capture the image as everybody else does. Iris to do the pre-processing, the rotating, the deslanting, the desmiling. That's all, you can do that very straightforward. And Visual Spec, the spectroscopy software, is free as well. RSpec has a nice function where you can kind of do this all semi-automatically, but is it $100 or $100 for the license, and even that only lasts a year or so before they issue an update and go give us another $100. So Visual Spec win hands down. So it's very straightforward. That's just a few you can see. There is stuff turning up all the time, so you're actually, I don't want to use the word frontier, but you are on the frontier. These unusual captures are the thing that make it worthwhile, because they're the ones that are out with the showers. They're the ones that actually tell us something about the bigger meteoroid environment in which the Earth inhabits. And for me, it's a fascinating pursuit, and I encourage anybody to give it a go. It's a very, very straightforward. So that was a bit quicker than anticipated, but we're running out of time. So there we go. Thank you for listening.
Any questions?
What's your thoughts on the alignment of the diffraction grating against the pixel array? Do you have them running parallel to the vertical horizontal axis, or?
You could argue efficiency-wise that it's best to be perfectly aligned.
Right.
But I've found that domestic environment where you've got street lights and other sources of rubbish, I find a very slight misalignment can help sometimes, just with discriminating between different sources, simply because you've got a misalignment. But in principle, the dispersion along the longest axis will catch you more meteors simply on a unit square area basis. The other thing which I use by deliberately misaligning is the moon. Now, diffractions gratings by their very nature diffract light, and the moon can be there and you're pointing that way and you've still got an enormous big band in your capture. So sometimes you can rotate the grating and the moon's interference won't disappear, but you do lose some of the ultimate efficiency. The other issue is that, and this is one of Peter Jenniskins, another meteor expert who works for the SETI Institute. Again, optically it is correct. You can tilt the grating with respect to the objective so that the first order is optimally recorded. But again, the gain of that versus the complexity of cobbling together an angled mount on a flat surface, I just don't think it's worth it. Because that version of the Geminid, and that was just stuck in the front. Because the other issue is that in order to take advantage of that tilt, the meteor must fall in exactly the correct place, otherwise you lose the gain. Right. So I don't think it's worth tilting it.
If it was me, if it was me, if I tilted it one way, you can be sure the meteor will go the opposite way.
Well, that's the good thing about showers is that as the Earth rotates and the radiant changes position, you can actually rotate your grating to optimise the chance of catching a correctly dispersed meteor. But with the sporadics, how did we go back? that was slightly tilted, you know, the dispersion was that way, but the meteor ran in at an angle. And the more meteors you capture, the more of those you get. There just seems to be some power of nature that will always send the meteor the wrong way with respect to the dispersion axis. But that's just something you have to tease that I've discovered over the past 5 years or so. Is that it's the sporadics that are the interesting thing, the ones that have been dispersed over time, the ones that have, you know, been shed into the kind of larger background. They're the ones that throw up the unusual. Because there was Alec had recorded this one as well, and just with a single station observation, it was a Perseid. It possibly was a Perseid.
The single station, possible
Perseid.
There's always that question mark, isn't it?
Yeah, exactly. And this is one of the good things about, because, well, that's one example. The other one was the quadrantids and the delta draconids or alpha draconids geocentric velocities. So
December alpha draconids.
That's the one. They have very similar geocentric velocities. So if you're observing it, you would just see it and you go, well, that was a quadrantid. But if you have the spectrum, you can do this thing that I call comparative meteor spectroscopy, where if you've got an established group of spectrum from a particular shower, you can say, well, no, that's not a Perseid. So again, unless you had the spectrum, if you saw that under any other circumstances, you could wrongly assign it. So the spectroscopy actually allows you to eliminate false meteor catches within streams, which is, again, to me that was an unforeseen event, and all of a sudden you think, God, you can do this. So it's a very powerful analytical tool in that regard.
And for building up larger and larger, you know, among sample databases essentially of these, where you refine that, and then you said there was 17, you have another one now on top of that. And
yes.
Just refine it even more.
Yep. And the other thing is that when I was reading the paper, that's let's see. You can see that apart from the subtle difference in the broad spectrum characteristics, but there are more peaks. And that's because this was recorded with an 830 line per millimetre grating as opposed to a 600 line per millimetre grating. Now, the work that Jerry had done, in fact, I had emailed him just the other week there about this, is that he's still using image intensifiers. Now, image intensifiers get you magnitude, but they lose you resolution. So again, if you were comparing one spectrum to the other, and you have that as opposed to that, are these real or is it noise? Whereas you can be confident they're probably real. So because they are rounded and the lines don't exist. And at one of the IMCs, I don't know if let's go right back to the start, that one there. One of the downsides about gratings I should have mentioned is that whilst they're very useful in their utility, because of the nature of diffraction, they produce multiple images of the spectrum. So you get what they call the zero order, which is the meteor, which in this case actually fell just outside the field of view. This is the first order. You have the second order, the third order getting fainter and fainter and fainter, but the dispersion gets wider and wider and wider. So the first order is usually clean, but sometimes the second order overlaps the first order, and that just progressively gets worse. And again, that's to do with the diffraction of light through the grating. But in this one, I don't know if you can see, there's a very faint line there. That is actually the magnesium line from the second order. And at one of the IMCs, they had got a beautiful spectrum, a gorgeous spectrum of Perseid, but it had dozens of lines in here, and they were absolutely adamant that it was atmospherics, oxygen lines and nitrogen lines, because they do match up with laboratory examples. But it wasn't. It was the second order overlap, because if you divide the wavelength by 2, it was the calcium lines, and they had them as 2 oxygen lines when it was the second order of the ionised calcium. So you need to be wary. If you start seeing extra lines, yes, they're real, but they might not be what they think they are. But experience in practice, and it's also a cautionary tale of how to interpret laboratory and library reference spectra. You need to know what your system does, and that just comes with observing and getting more and more spectra.
And are you more likely to get that overlapping if you use more lines per millimetre ratio.
Yes, it's one of the consequences that then let's say a 300, you'll get a really nice, bright first order, but because of the angle is slightly less, the second order will be a bit further away, and it's not until you get up to maybe the third or fourth orders. Yeah. But if you've got, an 830, an 830, or 1000, you really push it, then the second order begins to impinge already. But that'd be, so that's 777.4 nanometers. It's a very distinct oxygen. It's actually 3 lines. This is a triplet, that's a doublet, and that's a triplet. But at the very zip, blah, 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 blah. I came very close there to resolving the magnesium, very close. And that's when you know you're down. If you're down below, in a sort of standard Wattek system, if you like, you can get about a nanometre per pixel. So you'll see these lines, and something I've been trying to do for a long time. But that's something you need to be aware of, that when you look at laboratory spectra, you think, well, you can misinterpret it. You need to be careful in interpretation, because these are derived under very precise conditions, whereas every single meteor spectrum you take will be inherently different. No two spectra, even from the same shower, will be identical, simply because they're in different parts of the sky, different absorption. It's a minefield. It really is. But that's part of the challenge. So hopefully you can see it's complex, but it's not complicated. Or maybe that should be the other way around, I don't know. But it's very straightforward, and it's worth having a crack, even if you just do it during a shower, to see what your system can do. And as I said, the plastic gratings, you can get them, they tend to be sold in lines per inches. The Edmund stuff's is the common material, and I think it's 12,500 lines per inches or 25,000 lines per inches, which is 560 and 1,000 and something. Go for the lower count, because you will tend to get a brighter spectrum because you're dispersing less. But that's the cheapest way to do it, and just try it. Just stick one on your system, let it run through one of the peaks, and see what you see.
So I know 4 people in the British Isles who are currently doing this.
Yep.
So like yourself, and the way I push. Do you know anyone else?
Nope. No.
So how quickly can we get a database, the date and the time? Is there anything about the NEMETODE database? Just to confirm whether or not we've got an orbit for that, because I suspect that a number of us have got spectra, but we haven't got orbits for those. We don't realise we have an orbit for it, we don't realise it's
because what I've been doing is working very closely with Alex, because we now know we have an overlapping field. And same with David's. When we got that very first result a few years back, it was just we had agreed. We were quite close together, so the orbital solution wasn't brilliant, but it proved the concept, and that was another first. So it's just a case of emailing Alex, did you get this? A zero order or a spectrum?
Well, there's quite a few spectra that have all recorded over the past few years.
Yep.
And,
so is there any European database or catalogue of this, like the orbits?
No, that's one of the things that was discussed by Jerry in his paper, and unfortunately for various reasons I couldn't go to the IMC this year, but there was a shop before it, and that was one of the things we're going to be talking about, because I've just been doing this for a decade now, and they asked me to go along, but I just couldn't make it. But I don't know, I've not heard any feedback from actually if that was resolved or not. But part of the problem is that everybody's spectra is different, simply because of all the variables. You could record the same thing as me, and it would be the same-ish. And that's the problem. Its absolute calibration is almost impossible, simply because...
because it's difficult, it shouldn't stop people doing it. And something like Edmund, which has got all these orbits in it now, would be really useful if they could just enhance that. To at least put a flag in to say that somebody got a spectrum.
Yes, exactly.
That's my point, that's what I'm trying to get to. To say, I've got a lot of spectra. I can look at the NEMETODE database and see what orbits exist for that. I don't know the date and time of all the spectra you've got, or yours, Michael, or Motion's either, so at least you can have a look.
It's not perfect, but just so that
exactly. I mean, it's one of these boundaries that is genuinely new, it's novel, that development is novel, because we can now do it reliably and repeatedly, and more and more stations do it. the results can only get better.
Yep.
Sorry.
At the minute, Bill, you're saying that when you have overlapping between what you and others and you haven't, so you're not getting exactly the same spectra coming out on the same meteor.
No.
You're not saying it's that far out. So
have we actually had a meteor?
That far out. So
have we actually had a meteor where we've simultaneously detected the spectral report on two different stations?
I don't know. Well, see, ostensibly the spectra should be the same. But the differences are caused by the atmospheric absorption and the respective observing geometry. So I might record, in fact let's just use that one, I might record that, whereas William, let's just assume it's the same meteor, but William may record that because it's further away from him, so there's more absorption, so he doesn't see the fainter line. I might get a beautiful spectrum, whereas William might only get, say, that line, and that line, and then that's when you to say, is it useful to compare them? But it's certainly useful to know they exist. But it's an observational variable that's impossible to remove.
equipment might affect it as well.
Well, exactly. I mean, well, yes, using a 600 versus an 830 or whatever, because the higher the line count and the grating, the fainter the spectrum is intrinsically. So to get the same magnitude, you need a brighter meteor. It's a minefield.
The case that, I've got one end of the spectrum, Bill's got the other end of the spectrum.
And that is another thing, is because, well, like the very last one, and the example, I use that because it's quite clean. There's just a few lines on it and it's easy to illustrate what's happening. But that's invariably what happens. You will only get a tiny fraction. Again, a posting on the BEA forum, I had one, it almost just looked like it was flat. I actually thought it was a satellite to start with, a satellite glint. But having recorded other satellite glints, they just record basically a line, a blurry solar spectrum. You can't see any detail in it, it's just a line. But when this just flashed, you just saw this group of lines light up. And they turned out to be all iron as well, but that was coming right at me, and it must have just ablated right towards me. It was astonishing. It was, I think you'd replied to the email, you'd got it really low in the horizon. Yeah. But to me, that was just in front of me. And again, it's just, you only, gratingly, a bit.
I guess that's the thing, if you're starting it, you're going to need thousands, really, because there are so many variables.
Oh yes, exactly. That's what I'm saying. That the expression I coined, the comparative meteor spectroscopy, it's just a relative comparison, but it's enough to say Perseid, not a Perseid, Perseid, not a Perseid. Providing the spectra are of comparable quality, as in you can see some lines that you can relate together, but you can't get absolute flux calibrations.
Yeah. Just wondering, given that you've got these two different incoming velocities, is there a sense of the temperature profile for these? Because different lines light up at different temperatures.
Yeah, well, that is actually what's been expressed there. Is that there is much more infrared emission coming from the atmosphere, and that's a consequence of the temperature. Yep.
But it's just like if you're seeing two different relative lights.
See that you're into a whole new lecture, because one of the things that I presented, and I did my PhD part-time for over a decade, was that I recorded both it was a Perseid and a random fireball, and if you rather than just look at the whole video, if you take the time and just step through the frames, you can actually see the spectra change within a frame, and one set of lines disappears, another set of lines light up, and that's as the fireball collapses, and the temperature is changing very rapidly with respect to the environment. So yes, you can.
Okay, so we also expect different temperature profiles,
yep,
and therefore different spectra.
Yep. Well, again, it was first highlighted again by Jerry Borowiczka, and it took a long while to reconcile what he was saying, because it was basically having the meteor at two temperatures simultaneously, and it's because it's a very when that particle enters the atmosphere, depending on its size and velocity, dictates how high up it ablates, etc. But how do you have something being at two temperatures at the same time? And it's again, that's an expression of the highly non-equilibrium dynamics that are going on, because the mean free path of the particles is in the order of centimetres, and it changes the meters, and it changes the way the energy is dissipated into the atmosphere, and that's a whole other lecture altogether.
I had two questions, I've now just got one. The first one was related to you basically confirmed the additional analysis during the trajectory
the flight,
of the thing. My second question was touching on what William said about the spectra and again the compositional lines. If the spectra were observed at two locations, and you had the meteor coming at you and going away from somebody else, is it possible with the resolution of the diffraction grain to see the
Doppler? No, because and this caused a raging debate at the IMC. A couple of years back. But when you do the sums, the delta V over V, to get a shift measurable at 60 kilometres per second, that's fast. But it's nowhere near 3 times 10 to the 8 metres per second. So you would need to measure down to some ridiculous fraction of a nanometer to see it.
Is it possible to get the most fantastic grating, or is it lost in the noise?
If you get more and more dispersion, you get fainter and fainter and fainter, and your noise level comes up, and it's unlikely you'd be able to record it.
Right. But what you can get from the flying division data off to long-video cameras, for example, is you can work out the deceleration. Obviously, you're working at the speeds coming into the atmosphere, but if it's lasted 3 or 4 seconds, you can determine the change in velocity from the start of the to the end of the flight. Okay.
It goes from 60 kilometres per second to nothing. And the actual G-force that's on those particles, that's part of the crushing force, it's astronomical. It is literally astronomical.
The change in composition as it's coming in could be, it's happening instantaneously, but when you were saying about, say, lactic sodium, and that might have been because the sodium was lost millions of years ago.
It's not, that doesn't...
As it's burning up.
Unlikely that you would, because you can see, okay, let's go back again.
So change in spectra.
So temporarily, you saw the videos, the meteor's going in that direction. You would see, say, nothing there, and then all of a sudden something appearing there. That might represent a compositional change. But as far as I've seen, you will see ones which are slightly shorter, but I think that's just because the lines are fainter with respect to the other lines. I've never seen any that have done that in the main flight. I've seen the changes after a terminal flare, and that's to do with the thermodynamics. It's not to do with the composition of the meteor. It's usually the interacting with the meteor head, and you'll just get that little overpressure. It's a shock that builds up, and that gives you enough thermal energy to excite some of the lines. But they're not changing as such as the meteor traverses the atmosphere.
A relative ratio of, say, a pair of lines, do they ever change? They
can, but not by very much. Not enough to say with confidence that it is a compositional change during the flight. That little particle is pretty much what it is all the way through to its untimely demise, when it just becomes sodium atoms for guide stars, or condensation nuclei for NLCs. Who knows?
There's a BA's got a spectrum database. If that would have been any use for me.
No, I spoke to, was it Roger, down in Newcastle, and that's one of the conflicts, is that these are uncalibrated.
Yes.
You can't get it to the standard of a uncalibrated.
Yes.
You can't get it to the standard of a stellar spectra, and it's a different beast. You can apply all the techniques you want, but you can't guarantee. You can observe the same star over and over and over again, and you can refine the calibration with standard stars and what have you. You can't, because you have no information about the particle that's coming in. All you see is the end effect, and it is just what it is. and it's very annoying at times.
The second one, another quick one, was when we submit some of our quality light curves for occultations where there's been an atmosphere.
Yep.
Paris. Like with CCD work, they ask for flat field and dark frame videos, and we can do them and can apply them. And it may not make any difference, you know. The video can do it. If ever anyone asks,
there would be. I think there would be some gain to. I've tried it, and with not much success, I have to say. Of generating, because you can do it in iris, you can generate a synthetic flat field, which will compensate for the brightnesses.
The software I have fully supports video, flats, darks, minus.
Oh well, it may be very well, but I'll email you.
That makes no difference, but if you're professionally challenged about that,
but
tested.
But that could make a marginal difference. But again, in terms of because of all the other variables, it's the way down. It's just the nature of the beast, right enough. So I'm saying it is equally frustrating as it is, because it's actually such a powerful tool. It is the key physical, astrophysical, astronomical, geophysical technique. But just can't quite do it.
The skies are returning now, the darker skies, let's see what
Speaking of darker skies, maybe before the sun sets completely.
That's the good thing, once you get people talking, we could be here till tomorrow.
Thanks very much for your time for all.
My pleasure.
Okay.